Another concept that we are going to discuss today is the temperature effect. So let's start with the temperature. So everyone should know that if we have a hot, right? If it's hot like summer, then the materials expansion. And during the winter, it's cold, it will be contraction. So if the weather is cold, then it will be contraction. And for the civil structure like bridges, on a railway, all of that, and you can see exposed to outside temperature, and the daytime, the noontime, it's very hot. In the nighttime, it's cold. The change in temperature, it can be 10 degrees, and that change will change the length of the structure, and will that change for that temperature may increase the additional load, additional stress on the structure. So with that, we have to consider that temperature effect on the stress, on the load of the structure. So with that, let's have a constant that we have it coefficient of thermal expansion for temperature. So that either alpha T, we call that a coefficient of thermal expansion. Or contractions, and that alpha T is measured by what is the unit of that. So we have the unit depends on customary unit or SI unit. If it's customary unit, it will be inch over inch, and then over degree Fahrenheit. And in the SI units, it can have it millimeter over millimeter. 1 millimeter we use because normally it's very small expansion or contraction over not Fahrenheit, but it degrees Celsius. So those are the unit you have. So with that, we have go back to the appendix B that we mentioned earlier. For different material, for example, steel, you see the very second last column, they have it coefficients of thermal expansion. For this one in degree F, so and 10 negative 6. So for steel, for example, 6.5, 10 power negative 6 for 1 per 1 degree Fahrenheit. And if it's SI unit, you can have for steel, structural steel 836, it will be 11.7 10 power 6 for every Celsius degrees Celsius. So with that, we can continue. You can see how to find the alpha T coefficient of thermal expansion in appendix B. Depends on the SI or US customary unit. And from that expansion, you can see when the expansion or contraction, that total we call deformation, right? This is basically the deformation. So if we can see that that one is deformation of the body, and that deformation creates the strain. So from that we can have actually the temperature increase can create the strain on the body, so that we can have strain, and this case normal strain per 1 degree delta T, right? Per degree delta T. So if we want to find out the normal strain, epsilon, temperature, then it will be for coefficient of thermal expansion for every degree, so it will be alpha T how many degree change? Excuse me. We can time delta T. Okay, so if you have the material, and we know the coefficient of thermal expansion, then if we know the change in degree, for example, 10 degree, you just take 10 times the alpha T with the correct unit, US unit system, customary units or SI units. And when you have epsilon, you can find delta, because the deformation delta basically equal to alpha times the L naught. So we can have the associated deformation, whether expansion, red that I have, or blue contraction in here. So it will have the deformation for the materials. It will be epsilon temperature time epsilon due to temperature time the L naught, or equal to coefficient of thermal expansion time delta T and time L naught. So that, and this, all of this equation, if you forget, you can see that in the RDC, reference data card. Okay, reference data card. So RDC. So if I can show that in here, the reference data card for this mechanics material, you go to here, thermal deformation, you have the deformation equation for that delta equal to alpha times L, original length, delta T, which is T minus T0. So from that, go back to here. Now we have the temperature effect. And then what happened? For remember that they have both the load and the temperature change. For example, if you have a bridge and they have a load of the weight, the car, etc., and then the temperature change day and night, so that create another strain. And as you can see, another strain, it means create the stress on the material. How can we consider that? So let me go to the topic that here before we move on to show the worksheet problem for C. So total deformation of cowl member, Do you recall what is cowl member that we mentioned in the very first lesson? Cowl member is a centric axial loaded member. So what is that about? If we have a member here and assume it in tension, so you have the load P apply at both ends, and that we call it cowl member, right? And now, in addition to the load, we have the change, delta T, temperature. So between day and night, then it creates deformation. So as you can see, the deformation here combine the deformation due to the load and the deformation due to the temperature. So in other words, as you can see, the total deformation total, it will be equal to the deformation due to load P, plus deformation due to the temperature. Okay, so if, for example, these scenarios, if the temperature increase, then the deformation is, for temperature is positive. In this case, the load is in tension, so the delta load is positive. So both you can add. But sometimes if the load is in tension, that the body tend to increase the length, but then the delta T is negative. It means you reduce the temperature. The body tend to contraction due to the thermal effect. So the delta temperature is negative. So as you can see, when you add, but you have to consider the side of the deformation due to load and due to temperature. And from that equation that we learned earlier, we can have delta total equal to, due to load, if you recall for the car member, that is delta equal to PL over AE for the load, and then due to the thermal, it equal to alpha T delta T L naught. So from that, we can write down it equal to P L naught over AE, that for the load, plus alpha T, coefficient of thermal expansion or contraction, the change in temperature, and time L naught. So from that, we can box for combine both deformation due to temperature and load. And then keep in mind, each delta can be positive or negative. So let's go to worksheet for C to practice this. And you also have worksheet for D to have consider the thermal expansion as well.